Okay, we'll begin with problem 5.1, which is A through D, and we need to give an example of the following. So for part A, we need to give an example of a closed set without a maximum element. I chose a set of real numbers because a set of real numbers is both open and closed, so it is closed. And the set of real numbers is also infinite, therefore there won't be a maximum element in the set. For part B, we need a connected set that's not compact. I chose a set of the intersection of the set of real numbers and the interval 2 to infinity, because this can be split up and it can be written as E equals A union B. We can see that, but we can also see that every element is in this set because the numbers are real numbers. Therefore, it's connected. While the upper bound here is heading to infinity, we can see that it's not bounded, thus it's automatically not compact. For part D, we need an open set that contains a set of rational numbers. I chose real numbers once again because they're open and closed, so we know that it'll be open. And then Q, or the set of rational numbers, is contained in the set of real numbers. So there's that. For 5.2, we're gonna prove that if g prime of x is greater than 0 for all x in the interval AB, then g is an increasing function on AB. Well, since it's differentiable, we'll know that is continuous as well. So that gives us the criteria to use the mean value theorem. And the mean value theorem says that if that is the case, there exists a C in AB such that f prime of C equals f of B minus f of A over B minus A. By the given, we know that that is greater than 0. Thus, we get this to be greater than 0. So then, I'm gonna set that there because I don't know if you could see it. So there's that. Moving on. So then we can see when we move the B minus A from the denominator, we multiply it by 0, which equals 0. So then we get f of B minus f of A is greater than 0. We move the A over, therefore f of B is greater than f of A. By the definition of an increasing function, by looking at this, we can conclude that f is increasing on A to B. Okay, now for 5.3, considering the function f of t equals 1 over t on the interval of 1 to infinity. So obviously we're gonna let e greater than 0, arbitrary. And then we started with some scratch work over here. We obviously know that the absolute value of f of x minus f of y is less than e. And from there we can plug in x and y. And we do a little work. We pull out the x minus y because that's what we need for delta. So then we have 1 over xy. Well, with our bound starting at 1, we don't have a variable. We usually use a to plug in. So instead of a being there, we're going to plug in the 1. So in doing that, we end up getting delta equals epsilon. So then if we have xy in the interval 1 to infinity, and we know that x minus y is less than delta, then we use the scratch work that we got from over here And the conclusion is E. We did get E, so that means the proof is done, and we have proved that f of t is uniformly continuous in the interval 1 to infinity. For part B, we're going to find the derivative using the definition of derivative and plug in 3 to see what that value is. So we're using the definition of derivative from the book and from our notes. So then we get the limit as t approaches 3, because we want to find f prime of 3 is f of t minus f of 3 over t minus 3. Well, we do a little scratch work here. We plug in the values. So f of t is 1 over t. Then if we plug in the 3, we get 1/3. And we have t and minus 3. Yes. Okay, so we do a bit of work. We get the same denominator here. We pull out a negative because then we can see that the denominator cancels out with this numerator, and we end up with the limit of t approaching 3 of negative 1 over 3t. Well, if we take the limit of that, we get negative 1 over 9, so there's our answer. So then we consider this function on the interval, same interval we've been using, and we want to know what is L of 1, we want to know why is L differentiable, and what is L prime of x. So by using that definition, we take the integral of 1 over t, and we take the antiderivative because of the interval, and we get the natural log of t from 1 to x. Then we get natural log of x minus natural log of 1. Well, natural log of 1 is 0. So then we get L of x equals the natural log of x. So then if we plug in 1, natural log of 1 is 0. So, and we can see that by the fundamental theorem of calculus. If this is the case, which we can see here, same thing, then we know that the derivative of that is equal to the function, the original function of x. So with that being said, we had 1 over t, we plug in the x, we get 1 over x. And then we know L is differentiable, again, by using the fundamental theorem of calculus.